Hello again. Now this video is about classification. So in the difference between classification and regressions, that classification you want to isolate the points or the data points that you have into groups. Basically, you want to form like a shield between different groups to say everyone on this side of the shield would be in group A, everyone on the other side of the shield will be not in group A, so it might be in group B or C, depending on how many classes do you have. So we'll start with few imports. It's all the standard things that we talked about before. Again, I cannot emphasize enough the importance of setting the seed to maintain reproducibility with your results. So we'll run this one. Now when we make a classification dataset, we will import from sklearn datasets a function called make classification. It's similar to make regression, but you will have to identify number of classes, number of clusters per classes, and so on. So pretty standard stuff. It will return x's and y's. X's are your features, y's are the labels that you have for every class. So they will be 0, 1, 2, 3, 4, and so on. They will be integers. When you call make classification, you will specify number of samples, number of classes. This means we have 3 different classes, so y will be 0, 1, and 2. Number of features, as we're used to in the make regression function. Make classification has a different variable here, which is number of redundant features. These are the features that are not really useful, basically because they are kind of a linear combination of other features. So if you have 3 features and the third one is basically feature 1 plus feature 2, this would be a redundant feature. The class set, this is the separation between different classes, so how far they are from each other. And the scale would be how big or small each cluster of points is, or each class is. Now another important variable here is number of clusters per class. So this means when we put it to 1, this means that we have how many classes? 3 classes, and each class have all the points gathered around the same place. If you increase this to 2, then you will have 2 classes, 2 clusters of the same class. So this means you will have, in this case, 6 blobs, 2 of them for class A, 2 of them for class B, and 2 of them for class C. And as usual, number of informative features. These are the features that do actually contribute to the label that is returned in the Y. So pretty standard stuff. And then we pack the data into a data frame. We'll set the column names, and then we'll set the Y. We'll add the Y to the data frame as well. And then we are ready to start plotting with the pair plot from Seaborn. Sweet. Now we have here, as you can see, 3 classes, and they are fairly apart from each other. We can also see that we have the correlation between these classes and the Y, which is your label. And we can see here, and this is very important, that all classes have the same number of points. So the classes are balanced, or the data set is balanced in this case. When we check the histograms here, we can see a binomial distribution, a bimodal distribution. which means that we have a dip in between, and this is the point where uh, classes are separated from each other. All right. Now, notice something here, that these numbers in y are actually numerical, and that's why we have the problem is formulated as a regression here when we plot it this way. But we can change the type of y to be a categorical variable, and this will allow us to actually have more information when we plot that. So when we plot that, now we have x0, x1, and x2, and the y's are actually colored here, and this will give us a lot of insight to see how the classes are separated from each other. We can see here that x2 has both classes, the orange and the blue classes, overlapping, and it's similar on the other side because it's symmetric. So let's do this. Basically, I'm returning the plot into a variable here just to avoid the Jupyter to actually write this part in the output. Okay, so let's also plot this into 3D, so we can see now where the classes are in the 3D space, and we have all of them fairly separated. If we look or project from one side, we'll see two classes overlapping here, and if we check on the other side here, we'll see the red and green actually barely touching, but they could be overlapping as well. Awesome. Now the next thing we'll do is to do a 2D classifier. From this we will import the logistic regression from the linear models, and we will rely on two features here, 0 and 1. Why 0 and 1? I just picked them arbitrarily, really, and they're both actually, because we chose all the features to be informative, they both are kind of enough to actually separate the data. Not interested in that. And now we can plot. We can have our model. We fit the data with this x and this y. We'll get the y hat to get mean square error, and so on and so forth. When we plot the figure, similar thing. The only thing here is how to color the points. So the way we did that is we made an array of black colors, and this format, this is something we can explain here. So when I say I can make a list like this, 1 1 1, this would be L1, for example, and this would be having 3 ones. You can also make it like that, 1 times 3, so this will repeat 1 3 times. So we can say L2 equals 1 and repeat it 3 times, then this would be 3 ones as well. So what we're saying here, we are creating a list of black colors and repeat it n times, which is number of samples or number of points that we have. And then we want to replace where y equals 0 with blue, y equals 1 with red, y equals 2 with green, y equals 3 with black, but we only have 0, 1, and 2. Now this notation, because some of you were asking about this notation, we can actually explain it as well. So if I have an x equals mp dot arrange, say 16, dot reshape. Let's do it -1 and 1, so it will be a column. So this is our x. Now if I say x equals 0, this will return true at the very first one and false at at the rest of them. When I say x, say mod 2 equals 0, this will return true for even numbers and false for the rest. So this is called a mask, so we can call this a mask. And if I say x sub this mask, it will return only the values coming from here. Now if I say x sub this mask equals 99, for example, now I'm replacing all the values at this mask with 99. So if I print x now, it will be 99, 1, 99, 3, 99, 5, and so on and so forth. So what we're doing here, we're replacing all the colors. We have colors in the uppercase C here. All the colors where y equals 0 or 1 or 2 with blue, red, and green. And now we need to get the minimum and maximum for all the features that we have, and then we'll create a line space for each one with the resolution say 25, and then we'll reshape with number of elements here, which is the res. Similar to what we did with regression when we plotted the plane, what we need is to create a mesh grid taking range 0 and 1. Actually, we don't need 2. I'm not actually using 2. So we can take this out. And this will give us two matrices where all the points span the entire surface of the area. And now let's get the boundary. The boundary here would be mainly getting the x grid range reshaped to a column, x grid range 1 reshaped to another column. We'll concatenate them, we'll get the boundary x. These would be the features that we will pass into the model. So we have now model.predict boundary x, and we'll reshape this to x grid range 0.shape. So it will become it will span the entire surface again, and this would be our y's. And now we can plot our x0 and x1, and then the boundary y will be the third one. Now the colors, we can when we plot, we can set a set of colors that will be picked based on the numbers or the values in y. So these y's will be 0, 1, and 2 because we have 3 classes. So zeros will go to blue, ones will go to red, and green will take the 3. And alpha equals 0 here, this for 0.5 here, this is for transparency. And levels here is mainly for the grading between the contour lines. So let's plot that. And there you have it. Now we have the 3 classes split, and now this is the boundary between the blue and the red, and this is the boundary between the green and the red. You can notice there is a slither of red between the blue and green here, and this is probably attributed to this red point being misplaced to the green one. It happens, it's part of the data, it will always be there. It could have well been the green actually spanning all the way down on this side, but it seems like the model fitted the data this way. Now let's take this a little bit further and let's make a 3D classifier. So with a 3D classifier, we are using the 3 features x0, x1, x2. And now to plot this, we don't have the luxury of actually having a surface like this to do that. So what we need is actually in this 3D space, we need to carve up this space into three different regions which cover the which encapsulate the blue and the red and the green. So the boundary between the different classes according to the model then will be a surface that carves this volume into three separate blocks. Now with um, with the 2D we can span on two dimensions. That's why we need mesh grid with two features. With the 3D we will need three. And not just that, we need a 3D matrix because we do not have pixels anymore. We have volumetric pixels or voxels for short. So the training part is fairly similar. We'll just use all the features in X and Y. We'll create a model, we'll fit the model, we'll predict, get MSE, and we can get the coefficients. And then make your figure, prepare your colors. All of this is the same, and this will be plotting the scatter plot of all the points and having the colors as they are prepared here. Similar thing that we have done before. Now we need a minimum and maximum x0, 1, and 2 for this, and we will create three um, ranges for x, y, and z, or for 0, x0, 1, and 2, and we'll reshape everything to res. Be careful when playing with this number, it will make the volume very fine and might run out of RAM. Now you are working on a three-dimensional space, not a 2D image anymore. And we'll use mesh grid. We'll pass the three things here. This will produce 3D matrix for each one of these. We again will reshape them into columns. We'll arrange them and concatenate. This will give us a list of all the points spanning the volume. Now, not spanning a surface, it's spanning the entire volume. And this is the same kind of feature vector that the model is expecting. It's three different features. Now with the colors, what we actually need to do is, so the way the volumetric rendering happens, that you split the volume into blocks and you just say this block is turned on or off. So this is how the plotting happens here. What we need here is mainly this is just preparing the colors. So again we are checking whether the predicted was 0, 1, 2 or 3, and for each one of them we'll set RGB colors and the transparency for the voxel there. And finally you will reshape the color vector here, which represents the classes that were predicted, into the same shape of x range 0 plus 4. These four spaces are mainly for the RGMB and the alpha here. It's the same size that we made the C here. And then comes the time to actually specify which blocks to be turned on and off for the rendering. And basically what we're doing, we're saying just we will turn on everything because we are specifying which class the voxel belongs to using the color. So we'll turn everything on. That's why it's asking for ones. So mp.ones, just like MATLAB, if you say I want ones 10, it will give you an array of 10 values. They are all set to 1. There is a similar one here called zeros. So here we're saying we'll get ones of the shape midpoint x grid range dot shape. The midpoint function here is mainly to just find the midpoint in the voxel and not being on the side. This is to adjust for the shifting there. And if you notice here, the Z grid predicted, we are choosing everything in it except the last element because we do not want um, number of points are number of points of the corners for each voxel, each cube. We want only the midpoint, so this would be dropping the last one. And finally, when we're plotting, we are saying plot x grid range 0, 1, 2, and these voxels will be turned on. In our case here, all these voxels are turned on because of using ones here. Where it shows which class the voxel belongs to is actually specified by the face colors here, which is the color that we built from the prediction coming from the model and adjusted and replaced where zeros, 1, 2s, and 3s with these colors and the transparency. So when we run this, we have a very decent mean square error here, which is really nice. So when we run this, you will have a volume. This cube is your volume. Notice it's fairly heavy when you rotate, and this volume is carved in a way that you will have the blue points falling into one space, and the green is in another space, and the red in the third space. Now when you look at this say this blue volume here, it says all this area, any point that falls into this area will be considered blue, any point that falls within this area will be considered red, and so on for the green. So this would be the plotting the boundaries between classes in 3D space. If you go higher in dimensions, say in 4D space, then we might need to uh, either make multiple of these figures, or you can actually slice through each through the hypercube, and each slice will give you one cube. So when you project from 3D space to 2D space, when you slice through a 3D cube, it will give you a rectangle. When you go from 3D space to 4D space, when you slice through the hypercube, it will give you a cube, and so on. I hope this helps, and I hope you can maybe try these visualizations in your projects. I believe they can add wonderful value to your reports. And thank you.